Thanks very much for coming out with this cold weather. It's great to see a few familiar faces, some that I haven't seen in ages. I'm very happy to see some of those faces here. Thanks for the organization, the background, Aaron and team, Nimbus for hosting this, and BAGIM for opening the doors. It's really great to be here. It's been a long while that I was last in Boston, actually. Today, I would like to take you along a journey that we did 15, 16 years now, and with BioSolveIT. We started from 0D, so where we have no structural information about any 3D of the ligands that we are working with, up to 3D, where we are currently embarking into actually working with these huge spaces in pockets. I'm not as keen on using lurid words like revolution, etc., but I think in this very case, it is a little bit justified. So let me introduce you to the matter. Too low, voice? Mic up a little bit. Mic up a little bit. Mic up a little bit. Thank you so much. Oh yeah, much better, right? Can you hear me back there? Thanks much. So being in Boston, I thought, why not quote Pat Walters? The most significant thing that's happened to my work over the last 5 to 10 years has been the advent of libraries like Enamine Real for synthesis on demand. So this is really something that has changed the discipline, and that's also something that we feel very deeply now in our business. Why is this? Why is this so revolutionary? Why is this so different? So let's take a quick look at how much costs a molecule if you want to make it in-house. And these are really very coarse values, big error bars that I heard from hearsay by interviewing clients and peers, etc. What they say is the US in-house compound, roughly, more or less, is $3,000. The European compound is $2,000, and a Chinese compound would roughly be $500 to $1,000. Very costly. So that's a lot of money, especially when you think about the fact that you will have to work with many molecules. So I stole this graphic from Soon et al. Down there in the Acta Pharmaceutica Sinica. And I found this very well displayed, stuff that you usually, I think, are already acquainted with. I want to not spend too much time on this, but what I want to spend time on is to focus on that SAW area. So that also, to me, was kind of striking to see that 99.9 something, again, an error bar will be in there, compounds are made in vain, but still all this consumes 30% of the total cost of developing a new drug. So that means that drug discovery being for the brave, we will have to think twice about the molecules that we synthesize and want to synthesize during that stage. So in other words, promising molecules, molecules that we hope to be able to take along that pipeline will have to be super cheap, if possible, the cheapest possible way we want to have these compounds. They must be easily accessible. They must be very quickly there. And ideally, that's the ultimate goal, certainly, we want to create new IP. We want to target a novel area in that space that we have hitherto not really targeted. So would the answer simply be, let's make bigger haystacks so that we have more to choose from? Well, let me take you back a few years when I was still in the lab, sitting on the heating, while I was waiting for some reaction to happen. We had these Sigma catalogs. Who remember Sigma catalogs? Don't be shy. I see a few nodders. Yeah, that was cool, wasn't it? I mean, we sat on somewhere and we were just reading this as if it was a book. Well, the properties there, the price info was really very interesting, wasn't it? And then Dr. Bates, mask wearer, she was, does anyone else remember the old Sigma catalogs? Gosh, I loved looking up chemicals in that. That's true, but regrettably, that's a thing of the past. We're now way, way bigger than these books could ever have been. And I took these figures mostly from numbers that were quoted at a late 2020, December 2020 symposium organized by the NIH on ultra-large databases. And this is elucidating. So before my marriage, there was a Vogue or Elle special or so special marriage. And on the very last page, there was how to blow the budget. And this is actually how you can do it. Yeah? So spend something on some million CPU hours, for example, and then you'll be able to cope with 10 to the 12th. And I'm not blaming anybody. I'm just trying to get the awareness up that at one point we can no longer enumerate things, and we can no longer work on libraries as we used to do, or on SMILES file where every line is one molecule. This simply will come to an end if we work on enumerated libraries. And that range is roughly 10 to the 12th, maybe 10 to the 30th or so, but 10 to the 20th, we will have to think twice how to actually cope with these things. And also, I mean, we perhaps feel this even a little stronger with the Ukrainian war now next door to us, but we feel a very pressing need to save energy. You know? And also from an ethical standpoint, it's really something that we should think twice about. Do we really want to do number crunching and heat up the computers if we have another solution? And we are seeking this solution. And the solution is then, once you think about it, in these cases, relatively obvious what you can do for the big stuff, and then what remains on an enumerated basis, you can still do classical stuff. Namely, we need to deal with the combinatorics. So we could do something like the click reaction, where you have an azide, alkyne, amine, form a ring cycling, and you would like to describe this in the computer. Then instead of enumerating everything there, we could describe it in the combinatorial way. So here I have put up these little Lego bricks to symbolify it, to show you guys that we encode, or we can encode, a compatibility between certain building blocks. That's really not rocket science, but it needs to be encoded at one point. So gray may react with red, but gray may not react with green, for example. These things we can encode and we can feed it into the computer and thus describe this combinatorial explosion in a very simplified way. So if we now take this idea a little further, what we then would need to do is, let's say we have some building blocks here on this side where we do have these functional groups explicitly still noted. We would have to transform this into what we call synthons at this point in time. I'm aware that people use building blocks and synthons and edarcs, etc., in different ways, but that's now, shall please but be now the definition for what we have currently. So we have the building blocks on there, that's a building, the functional groups on there, that's a building block. We describe this, the respective functionality in kind of an anonymized way, and that's what we call a synthon. And then we feed this into input channel number 1, and we take the reactions, and that's input channel number 2. And these reactions then will, using a linker compatibility matrix, describe a chemical space. And I will from now on use chemical space when I refer to some combinatorially set up chemical space, so a combinatorial collection of molecules. Just so that you once have heard it, the software that we have that does that is called Colibri. And then once Colibri has this processed and the duplicates, etc., have been removed, it takes care of all the bookkeeping. Naming is an issue. Naming is not so easy to take care of. Initialization, protonation, and stuff. And once we have all done this, or we have run through this pipeline, then we arrive at a combinatorially set up chemical space. So far, so good. Thanks very much for the feedback. So jumping a few steps ahead now. So I'll explain details in a second. Where do we stand today? So usually people refer to Regine Bohacek's paper, the ubiquitously mentioned 10 to the 60s. Well, I think she writes in the paper well above 10 to the 60s, and could also be 10 to the 63 or so molecules. That shall be kind of the number with which we deal when we talk about drug-like or therapeutically relevant chemical space. And you see, so we have in blue the commercially available collections of molecules. In orange, we have publicly available molecules or molecules that can be created using public information. And in red, we have proprietary information. It's a little bit hard to distinguish, but I hope you can still distinguish it, the red and the orange on this projector. And you see that, for example, PubChem is 10 to the 8th, roughly. You know, that's the collection of molecules. NCI-SEVI is 10 to the 9th. And then you see it already starts to get combinatorial here. We have Boehringer Ingelheim's compound library of accessible and innovative molecules. I think that's what BI claim stands for, 2012, with 10 to the 11th molecules, etc. And then if you combine public and private information, so the in-house information with public information, then you can really blow them up, these spaces. And currently leading the field is GSK with the GSK XXL space. that counts a formal number of molecules of 10 to the 26. So this is definitely no longer enumeratable. That's you can't do anything smiles with this anymore. So now seeing these numbers and seeing that these are set up and have been pumped up in a combinatorial way, this points to the fact that these should also be much easier to be synthesized or much easier to have. And look now at these figures here. Now we have the cost for an on-demand for one such molecule from these combinatorial on-demand molecules from these chemical spaces. Here we go down from roughly 3,000 to 1,000, a third. $200 for the real space molecules from Ukraine, from Enamine. That's a saving of a factor of 10, and we have 400 roughly for the galaxy molecules from Wuxi from their combinatorial space. So there is a massive amount of saving in this technology, which definitely must have aided to make this so popular as it is today. Coarse values again, and the very striking thing, at least for me, is that they really deliver these molecules. If you order 100, you get 70, 80, or even more. Enamine really never cease to surprise me with their success rates. I hope you also hear something similar. So how can we then search these incredibly huge spaces? Well, the obvious is, the first step is similarity. So I hold a molecule in front of the face of this chemical space, and I ask the chemical space, can you give me back what is most similar or what has a given similarity, a target similarity that I would like to achieve? But then I learned from Hugo Corbini that similarity certainly depends on the descriptor and what you would like to see. So what is more similar to an elephant, a banana or a spoon? It depends on the descriptor. If it's the color, then it's perhaps the spoon. If it's the size, then it's perhaps more the banana, even though the two are obviously pretty dissimilar. So similarity, it depends. And I would like to describe this in a pictorial way here, using a fisherman who has a net that is close to his body. It's just a meter long or so, and he fishes the molecules that are relatively similar to the ones that the query is. So high Tanimotos, as we're used to work with. So there is a methylene inserted, there is an oxygen for a nitrogen, also small modifications, the obvious, where a chemist typically would say, that doesn't surprise me, I would have sketched this automatically with these high similarities. Then again, there are these things where you throw out the network far, far away into the water, and you fish out molecules that behave similarly, but that look totally similar, totally dissimilar. So here is an example. Up there we have riluzole, potassium channel inhibitor. And what it picks out in high similarities here is, for example, lamotrigine. Forget for a second these numbers here, I'll explain this. So this also is a potassium channel inhibitor, and we have a feature tree similarity. I'll introduce this in a second. So a fuzzy similarity of 0.86. So a relatively high similarity, and still molecules that look very different. So depending on what we want to do, what we're up to, where we're standing in the project, we may want to fish close by, or we may want to fish further away. So I'm going to focus on this last thing for the next few minutes. So this is a technology which is stone old. It's from 1998, and we have this in our portfolio for a long time already, and we have further optimized it over the years. We have parallelized things, and et cetera, et cetera. And it was there for a long time. And it's funny that this is now taking off so strongly, and this must be because we are now coupling this to content. We had the algorithm, the machinery, and now with Enamine, Wuxi, and all these other compound providers, we now have very tangible, tough stuff to search with. Feature trees describe a molecule as a tree. From development programming, we love trees because we can cut them into pieces and then reassemble them, parallelize them easily, et cetera, et cetera. And this tree now contains information about the molecular parts. So rings collapse to blobs, and usually terminal atoms also collapse in the atom they are bonded to, but they are not at all 3D. I just painted it this way so that you guys can relate to, or can get the relation between the feature tree and the molecule. So the blobs contain phys-chem properties of the contributing atoms. And what's great about these is that they retain the topology. So we know that that carboxylic function back there is far, far away from that amine function on the other side, for example, where the classical Tanimotos would just simply say, yes, that's there, but I don't know how far it is from something else. Classical Tanimotos. So that said, if we now have such a feature tree, how can we then cope with these chemical spaces? So if you recall, chemical space is made up of synthons and reactions. These are fed into the synthetic process of this virtual synthetic process for a chemical space. So if we now have this query in terms of a feature tree, of this F tree, and we hold this in front of the chemical space, what we need to do, or what we do, is we cut this into pieces and we search this fragment by fragment. So we cut a feature tree into pieces, we give it a targeted similarity. So for example, find the most similar thing in that chemical space. And we find from all the building blocks that are functionalized with our little Lego bricks, for example, here, we call them linkers, we find this first piece, for example. And this first piece then may be a little larger here or a little smaller there, but essentially it's still green, green, blue. So it should have similar phys-chem properties, at least on the 0D level, if you wish. And then, given that this linker knows the compatibility with what it can go on to, we fish out the next one. This means that our search will take place on the building block level. It will not take place on the 10 to the very, very many level, but we operate on the building block level and use the compatibility to build up only what can be built up from this chemistry description that the chemical space was made up with. And then the next one, and then we spit out the similarity value. So this corresponds to this search. You can imagine that this corresponds to, well, one of us recently said it corresponds to Friday evening in a Costco, and you have your what is it called? The trolley? Is it a trolley? The shopping cart in front of you. And you go like, I gotta make pancakes tomorrow, so I need butter. And then you have tons of butter. Do you actually need butter for pancakes? I don't know. So you have various forms of butter, salted butter, non-salted butter, etc. And this is exactly the same thing. So if I stand on this side here for diversification, we start down here at the lower left. And we say, for example, let's start with these types of butter, which in this case is amines. So we first move along this axis through this description of the chemical space. And for example, we fish out, this one is the most similar. This amine is the most similar. Then we take the next axis. So we take the next island Costco and navigate all the way up here. And we take, for example, this acid, in this case, it's the acid functionalities to form an amide. And then we traverse, or we take the next axis, the z-axis in this case, to couple this, for example, to some cyclic system. So what we do essentially is we traverse a hypercube of possibilities, an n-dimensional cube of possibilities, which is very, very similar, almost identical, except for the complications, to protein alignment, so dynamic programming. Those of you who are very computational may be familiar with that. So you traverse a dynamic programming matrix and try to find the most cost-efficient way. And what comes out is, by guarantee and deterministically, the best possible result given the respective parameters like gap costs, for example, in protein alignment. Did I lose you? I lost a few. No, okay. Please interrupt me. So I flew all the way over so that you guys interrupt me and quiz me and poke me and whatever you're up to. So pancakes have lots of butter. Hopefully. I should practice. So the knowledge about what's doable, what's not doable is essentially in this hypercube of possibilities. So you can imagine, I'm going here to get this a little bit more balanced. So we have an area where things are not likely to react or cannot react, etc. So we don't even have to touch this. What this turns out to be, or what this turns out to mean for us in the computation is that we don't even have to look at all these other parts. And that makes it the thing so fast. So take-home message dynamic programming, that's what it's called, avoids huge parts of an in principle accessible space that you don't even touch in traversing this hypercube of possibilities. So the path describes the connections, and what comes out is the compound. So that was that. Now, switch gears, and I'm going to talk about the nearby similarities now. That was sorely missing. We didn't really have a good idea of how to tackle this with these huge numbers until Louis Bellman came around in Matthias Rare's lab in Hamburg and proposed spacelight. Spacelight has been published in 21, and it was an academic prototype then. And then we took it into the company, we rewrote major parts of it, made it even faster. Now it's doubly as fast as the academic prototype, haven't the memory requirements, etc., etc. So what's the principal idea in here? The principal idea is that we describe reactions that contribute to this chemical space built up as so-called topology graphs. So this is a topology graph. And if you look closely at these molecules here, you will see that there are Y's in there. So up here, you see, for example, let's assume we have such a building block, and this building block has the fate that it will be apt to create a ring. So a triazine here, for example. So we have these two Y's here. These two Y's can then be filled by this other building block that has three Y's here, for example, that can actually match this way or that way. There are possibilities in there. And there is an R here and an R there, so that this R and this R can actually form an amide bond there. So you hopefully get the point. This topology graph describes per reaction what the fate of building blocks could be. So that means we need to pre-process a database. That's what we do with SpaceLight. And then we can do classical Tanimoto comparisons with these molecules in these big spaces. It's extremely fast. It uses a few seconds really with a multi-billion chemical space, and it spits this out directly. So the space creation essentially means that we would have to create these topology graphs per reaction, one per reaction. We write this out into the database. And then when we navigate the space, we will have to partition, we will have to cut into pieces the query molecules according to every compatible reaction. And this will be stored, and then we will match. We will kind of sub-enumerate the respective matches using the topology graphs. And then we have to compare them across all these reactions. So across all these reaction graphs, and then we can spit out the results and get the hit lists. So here's an example so that you know what I'm talking about. Careful now, I will have different similarities, different similarities here. One is the SpaceLight, the classical ECFP4 similarities, if you wish. And the other ones will be the feature trees, so the further away similarities, the fuzzy similarities. So here's sorafenib. And I searched sorafenib and held this in front of Enamine's real space and asked for the top scorers. And the top scorer is the thing itself. It is actually in the real space, so you could order it directly from there. But the next best hit drops down to 0.85, 0.86 in Tanimoto similarity. And you see that the substitution pattern is simply different. 0.81, there is a methylene inserted. And what is kind of astonishing, but I did the computation again this morning to verify, it really drops so heftily to 0.8, almost 0.8, when you simply insert a fluorine. It will definitely give a different character to the molecule. And the Tanimotos are like a very sharp knife. And so they have a very steep drop in the similarity there. So if we now do the same exercise with vedzolinetand, and compare the Tanimoto similarities again, now using the real space, the Wuxi galaxy space, and the E molecules explore space, then the top scorers come out to be already at 0.64. That's a pretty low Tanimoto similarity. What I mean to say with this is this knife is so sharp that if the thing is not in the space, then you will dramatically, you would see a dramatic loss, almost a step function. Yeah, the similarities will drastically drop down before you actually get your first hits, and they will look different. So here, for example, the thiodiazole part is entirely missing. Here we have a totally different core in the middle. So very, very, very different molecules. Whereas if we now switch to the more fuzzy mode, here, for example, using the feature trees top scorers, we have 0.96, 0.97 almost, with a molecule that looks very different, but still you would recognize a few things. You see this, you see this, you see this, you see this. So the difference with these descriptors is the first top molecules you wouldn't find using the sharp knife. And the other molecules look very different already with the relatively high feature tree fuzzy similarity. So it really depends on your use case and what you would like to know. So in active learning, for example, we did something like hop far away, collect the close bys. Hop further away, collect the close bys. And so this would then correspond to switching these descriptors, for example. That's what the software looks like. So essentially, it's really dragging, dropping, press a button, and then you get the syntax output. That's what the chemists like, because then you can even decide, do I want to make this myself, or would I really like to outsource this? Okay, how is this applied in real life? Again, Boehringer were pretty much at the forefront with this technology. What they did is they used a bunch of query molecules. They fed this to the search engine, to this BI claim, to this compound library of super interesting molecules. They came out with a bunch of hits that they then superimposed using rocks. That's, by the way, a very good idea because the descriptor itself is not 3D aware. Yeah? So it's just a connectivity something. And it's always good if you can to have a 3D method that is kind of the afterburner. So be it docking, be it superposition, etc. They did filtering, design, and came up with GPR 11.9 agonists, very quickly. And I put this up because it's one of the earliest examples using the technology. But there is also something fresher. So here, for example, from China, which is really striking. Essentially, I didn't have to do much except copying and pasting the graphical abstract of the paper. They followed a similar strategy. So they use these molecules, these known molecules as queries, put them in a bucket, screened using the feature trees. They write enumerate here, but that's wrong. We found them up and asked, really, do you enumerate something? No, that's kind of a misunderstanding here. So they used the feature trees in a non-enumerated way, used all the available spaces, then docked them and came up with pretty active compounds, docked 50, the 50 high-ranking compounds, docked these and came up with active pretty quickly. So what is so striking about this exercise, in my view, is that they only required 6 months for the entire exercise, and they even have a mouse model in that paper published. It's amazing how fast they were. It's pretty striking. So that was similarity. Now I'm going to take you into the 3D world. Why not have a pocket and let the pocket pull, let the pocket pick from the chemical space those molecules that fit. We call this chemical space docking, and it works as follows. So we have the space, as I explained before, we have our combinatorial setup, building blocks in there, the synthons and the reactions. And then we only need to dock the building blocks in that space, which is usually in the range of a few hundred thousands. Yeah? That's not yet the combinatorics. We don't have to dock the 10 to the very many, but we can operate on the building block level. So we dock a few hundred thousands, that's easily doable. And then we have the compatibility matrix. So we know what those dangling bonds can do and what they cannot do. And we have filters. So for example, this one slams into the wall. That one doesn't really grow where it should. That one doesn't really form interactions and so on and so forth. So a bunch of filters that will kick out quite a few from these initially docked building blocks. And then we continue using the linker compatibility matrix. So we build up only that, what can be synthesized later by design. And we need a round, or we would want a round of visual filtering so that we can continue with the next round. And then after these 2 rounds, typically we're already done. And we have compounds that by design are purchasable. And that's really nice, because then, 3 weeks, 4 weeks later, I will have them on my bench. So first exercise, admittedly a low-hanging fruit. So we started out with the kinase with Genentech. We did this, and we were blown away by the hit rate. Yeah, that was a tremendous success. So Paul Barosa first reported on this drug space symposium there, but it's also by now published down there in Nature Communications. They sent these to testing, and they had a 40% hit rate. That was really cool. That was really good. With respect to the resource and this kind of green computing, if you wish, there is this graphic that he presented. So down here we have the number of molecules. He writes log, but that's a little typo if you look at this. So we have 3, 6, 7 here, 3, 6, 7, 8 there, 3, 6, 9 there, and so on and so forth. So these are the number of molecules on a log scale. And here we have the cluster days that they required to actually compute those. And the chemical space docking line is that cyan line, the one that stays down here, this one. Yeah. So obviously, it does not scale linearly because we exploit the combinatorics underneath. Whereas if you operate on enumerated databases, you see how this thing explodes. So these are just a few publications for people that used to dock a huge number of molecules. So this is definitely still ready to take some more molecules in the future. It's upcoming in Q1, so we're currently productifying it today. We would be happy to do this as a service, but I don't want to do advertising. So growing fragments into space. What I just said is an empty pocket picking molecules from the chemical space. We could just as well, if we are in the fortunate situation to have a fragment binder, for example, start from the fragment binder and grow from the fragment, right? So that's what we did with Gerhard Klebe's group and Crystal's first. I'll show you in a second, but the idea is essentially the same. So instead of an empty pocket, now we used an X-ray determined fragment hit. And I should stress at this point in time that the fragments would not have been found if we had used a classical assay-based screening strategy. So they were really so weakly binding that we wouldn't have had any chance to detect them. But X-ray did, and actually with a very nice resolution. So we picked 4 of those and did this exercise, went into the chemical space, used the combinatorics underneath, the linker compatibility matrix again, and came up with a bunch of hits that we proposed. So here's just one of those examples. So in blue, we have the X-ray, and in nude, we have the docking. So the first thing that you always will want to do is confirm the experiment by redocking. So that's what we did. The RMSD was super small, 0.3, so we're good. And we thought, okay, let's grow and let's go from here. So now we use this fragment in there and ask the chemical space, in this case, it was Enamine's real space, what fragments do you have in terms of your synthons or building blocks that are very similar to this fragment that we have? And we did not bind ourselves to exactly this fragment, but we gave it a little bit of leeway. So there is an adaptive algorithm that we implemented that kicks out atoms that are too far away. When we overlay them, does this again and so forth. So there is a little bit of leeway in there to also arrive at slightly different fragments. And then we showed this to the back then 2.6 billion Enamine real space. And we came out with 60 compounds that had a Ki better than 500 micromolar. And of those, very quickly, 6 X-rays could be obtained. The best binder was then high nanomolar, 744 nanomolar. But it did already have 2 stereocenters, so it was not something, super easy or so, but something where the chemist said, okay, let's do this. And this went along this pipeline that I just explained. And it was really, it was something that doesn't work like a classical technology where you usually have a funnel. So I wrote up there, ceci n'est pas un funnel, as the French say, funnel. So you blow it up in the middle. So we started out with these 4 fragments, then we blew it up, and then it came down again. And that's the chemical space docking workflow that we did. Yes, please.
You had 6 co-crystal structures in that. How many corresponded to the predicted binding mode, and how many surprised you?
The ones that we found all corresponded to the predicted binding mode. Yeah, I mean, I think it's not so astounding because when you have an anchor and grow algorithm like the one that we use, and you give the anchor as a starting point, then the Docker should be able to do a proper thing. It should not be, admitted, we have seen. In German, we would say we have seen horses vomit in front of the pharmacy. Very weird, but that's what we say. Wir haben schon Pferde vor der Apotheke kotzen sehen, as we would say in German. But in this case, that wasn't so surprising. Yeah? So the anchor was there, and we just had to extend it from there. Mm-hmm. Yeah. So it's not really funnel shaped, and any member of this multi-billion space could emerge a priori as a hit. Yeah, that was really well received. We made it on the top of the JMed Chem cover, and we were coronated by Derek Lowe, etc. So very super happy. Now, again, to something completely different. Similarity is great, docking is great, and growing is great, etc. But sometimes you're in the position where you think like, I'm so progressed in my project, I need this substructure, this exact substructure. Is this in the space or not? You cannot do this in an enumerated way when you have 10 to the 14th, 15th or so molecules. So you need something. And this is where, and Matthias Raray said, I've been thinking about this problem so long. And then came Robert, and Robert really cracked that nut. So he wrote up SpaceMax. And SpaceMax now does exactly that. It does the exact and maximum common substructure search in these combinatorial spaces. And it's super fast. I can actually demo this here on the laptop if you wish later on. I did a little movie that shows that essentially. You can switch the mode. So you say, I need this exact substructure, or you give it a little bit of leeway, and even smart support is upcoming here. So here's that example from the academic prototype that we have. So for example, if you search something like this, the substructure that we gave in there in terms of a smart expression that you may not see, this is tildes that I gave, so an any bond between those atoms, and they are small letters, so aromatic bonds. Do you have something like this in the chemical space? And then if we actually feed this into the command line, the first thing that we would have to do is call spacelight and give it as an argument. Well, -C means continuous mode. I want to interactively work with this. -F means what's the fragment space, what's the space that I should search. In this case, for example, the 2 billion galaxy space from Wuxi. And then when you hit return, it will first read in the space, so process this. And then you can give it a query. And this query would then essentially be some sort of smiles, or you can feed an SD file, etc., or a list of SD files, smiles files. And then shoot, I started it anew, but never mind. It's just running a few seconds. And then it processes this within milliseconds, really. It spits out those ranked then by the amount of goodness or the amount of quality of the substructure, and spits this out. So what you see here is it says the match is 8 atoms, whereas our query had, our query has 9 heavy atoms. We match 8 out of those with a molecule that has 13 atoms in total. And this similarity, forget it for a second. Here's the hit molecule. And now the nice thing is the hit molecule has a name. And this name you can copy and paste and send it off to Enamine or your partner that is behind these molecules, and ask for a quote and have this synthesized. So that's pretty impressive. It is really, really fast. And it gives you new power. So think, for example, about the idea you draw something and you feed in the smarts that lets you exchange 1 atom in this molecule that you feed in. Then you're already almost at Amazon for molecules. So if you like this molecule, you might just as well like those molecules where you just have an exchange of an atom or 2 or so. So that's a pretty powerful thing. So now I would like to be, I would like to prepare the discussion. Where do we stand time-wise? That's okay, right? With a few perspectives and report back to you what we are being asked also. So is it really bigger haystacks, more needles? Is that really so? And we have now many, many indications that this is actually true. Yeah? So one of the first indications was here, and Woody and I already chatted about this. That's a few years ago now, here 2018, and it's also published. Here we have the number of hits that they found at AstraZeneca when doing the exercise still on an enumerated basis. So they had a subset of their 10 to the 15th chemical space. They enumerated a subset and looked at the number of actives that they can find within this given amount of chunks that they had. And the larger the chunk, so we have 10 to the 5th here and 10 to the 10th up here, the larger the chunks, the more actives you find. 10 times larger, 10 times more actives. But then again, I should be standing here then, you see the number of scaffolds that starts to converge. Yeah? And this comes natural because the number of scaffolds is limited by the number of building blocks, plus a few perhaps ring-forming reactions, but these are also then at one point exhausted given the building blocks that we have. So that was the first indication where we thought, yes, it is indeed the case. And then you may have seen those on this paper here from you, Scheukert, Irvin, Enamine, etc. Ultra-large library docking for discovering new chemotypes. That was a linear docking exercise where they also discussed this in detail, that indeed bigger is better. And the editorial to this very article actually covers this, and it puts the focus on that it is what they find. What they also discuss in that paper is they see that more dirt is surfacing. Yeah? Who has seen that paper? Who recalls this? I don't want to bore you. A few. Okay, so it's a great paper, no doubt. So what they claim in there is if you make this haystack large, then the dirt also has a chance to surface, which at first sight makes a lot of sense for the enumerated methods. We, however, did the same exercise to look at, do we actually contaminate the hit list, the upper ranks, the first ranks, when we do the pull out with the methods that I just mentioned before, the non-enumerating methods, and we find exactly the opposite. And this is because we don't look at every piece of dirt, but we filter by the technology, we filter automatically out what cannot really fit. And this is why, for example, artificially high scores are much suppressed when we do the combinatorial docking instead of an enumeration-based docking. Yeah. Then a question that I hear very often, don't they overlap? They are so big, there must be tons of similar stuff in there. No, definitely no. So again, a student at Matthias Rareich's group wrote up a tool, a helper tool that does this space compare, where you can check how much how much overlap is really in there. And that, I mean, that it was small, we were hoping and thinking, but that it is that small, we were really amazed. So if we compare the real space at that time to 20 billion with the galaxy space, 2 times 10 to the 9th, and the knowledge space, which is a space that we do ourselves using public building blocks and public reactions that pumps up the numbers quite significantly. Only not even 3,000 molecules are shared by all 3 spaces at the same time. That is, I mean, it's very, very little, isn't it? Also, if we use other spaces that we compare, Ottawa's Cambria here up there, for example, again, 76,000 or so. Why can this be? Well, if we take twice 10 to the 14th, we still have 10 to the 14th. Yeah? So we're perhaps not used to thinking this way, but what's half of 10 to the 14th? It's still 10 to the 13th. So it's still a drop in the ocean. The overlap is almost non-existent between these chemical spaces. Sometimes, of course, that occurs, but it's really rare. So it's really worth to not only look at one chemical space if you hunt for new chemical matter in a certain area, but also look at the other spaces as well.
Sorry, the overlap, you mean the exact match?
Yeah, exact molecular match, yeah. Thanks for asking. Next question is, will I really have these compounds on my desk? And I mean, this is still, this has an error bar, and I can only report on what we hear. We ask our clients, we talk to people, and this is not necessarily stuff that people have found with our software, but also real compounds are available with enumerated methods as well. But what they report is really that the success rate is usually or has been around 80% or even higher since February. When the bombardment started, it has dropped a little bit, but still they are in the range of 70 to 80%, and they are still in the range of 6, 7, 8 weeks roughly, which I think is really still amazing given the circumstances under which these compounds are currently made in Ukraine. So time and money savings can really be substantial. I alluded to this already, and I just have a copy of a slide that Merck showed at a Merck internal conference at Darmstadt, Germany in 2018. And they applied this. So those of you who know Friedrich Rippmann, for example, have a chat with him. They applied this across 12 drug discovery projects with 1 to 4 experiments each. And they came out again with 80% feasibility of the molecules. They were 2 times faster than before, and this is extremely, I mean, that's almost mind-blowing, 90% savings, high IP by design. So they really embark heftily on these methods. They are now very happy with that. Okay, stop at this point. Again, switching gears. I know that many of you will be spending hours per day thinking about AI, support vector machines, machine learning, etc., etc. So I would like to give you a little bit food for thought, because I would like to report what clients and users of the software have already done in the context of AI with it. Essentially, I'm going to read this and try to see whether this resonates with you. So what people do is they train generative models using the distance to purchasability as a metric. They use DELs to train a machine learning model, then screen chemical space compounds, order, test. Very interesting combination, because that's also combinatorial. Generally also, it's about the last mile. So hop from the generated, whatever is in front of your in front of you in the computer, in front of your face and on the screen. Okay, that's nice, but where can I purchase it? So do this little last hop. Yeah? How can I get this on my desk for the user? Train your own building blocks and the reactions and find out what building blocks might be good for what reactions so that I can create an own combinatorial space. Or train the complexity and create bespoke subspaces. So for example, something that has more complex reactions where the compounds may be more expensive, something for later stages potentially, or something which is cheaper. That's also what clients do. Yeah, for example, the on-the-shelf space versus the take somewhat longer space. Or train and predict costs. Also very interesting. Managers like this and propose the cheaper to make before you make the more costly hits. Sometimes also you may have, rarely, but you may have multiple ways to the same compound. And then certainly you will want those that are cheaper to have. And put your idea here. Yeah? So happy to discuss and see whether that resonates with you. Okay, with this, I'm essentially at the end. I would like to have 2-3 slides where I just mentioned that there is a chemical space club on LinkedIn, which is co-maintained by BASF and the NIH. We have 640 or so members already in the LinkedIn club. There are discussions, presentations, paper mentions, etc., early announcements. So happy to let you know. Just take a photo of the screen if you want to have the number. Otherwise, it's 900-40-52. And then I would like to announce that yesterday we signed an exclusive agreement with Enamine on creating the best of both worlds, essentially. So they really, really know how to make molecules, and we have the algorithms to actually run through these chemical spaces to navigate them. We're embarking on creating really the most advanced navigation platform to be, hopefully. And we will create much bigger, larger spaces for you. There will be tailored software to be written. And so this collaboration is much, much reinforced and strengthened. That's it. You made it. Thanks very much. We still have plenty of time to actually talk and discuss. So now BAGIMers, help me. What's the tradition? Well, microphone goes from A to B?
Questions right now, and then we're just going down the street to the city. We have a thing that BioSolveIT minutes to help us set up. We're just out the building to the right. You can get to, and I'll open up the first question.
CityTap is the place. Yeah.
So one of the issues with points on to search, and sometimes those are hard to get to and codify. Sorry, this is a question about when you try to pick a space that you don't want to enumerate because you don't think the reactions are going to work. Those rules can be quite complicated and variable depending on the conditions that you're actually doing the synthesis in.
Yeah.
So are you getting those from Enamine using their enhanced building blocks? Are you doing them yourself?
Yeah.
Just curious how you're tackling that problem.
Yeah, thanks for asking. So Enamine does not disclose this to us. So they have our software to create the spaces and we get the package, and that's essentially it. We could probably, but that's not really our business. But I do know of other clients who use exactly what I had on that slide before. So to get a grip on that, or to get a handle on that, they feed this into a learning machine and let the machine predict whether this combination between building block and reaction will work or not. And then typically, Enamine also do this, that's published, they have thresholds for both. Will this building block work with this reaction? And will this reaction yield something at all? And these two combined thresholds are usually used as a heuristic to actually get forward with, should I include it or not? That's the state of the art to the best of my knowledge.
I had a question about dirt in the haystack, which I thought was a pretty nice metaphor. And I was curious, with even sort of your sort of reaction-based approach, like how does that exactly avoid sort of this dirt in the haystack if you're not, let's say you don't have an anchoring building block to start with?
I wish I had a whiteboard because that's exactly what, for example, dynamic programming is about. Okay, I'll try to symbolify this with my finger here. So imagine you have two protein chains and you would like to align them, and you have some capital A to capital D, and you have a small a to small d. And now you would like to align them. You could align them this way or that way. You know, it doesn't usually make sense to align proteins with the wrong directions, but let's assume these are then later molecules that you can very well align this way or that way. Yeah, but let's stick to the simplest case you have that way. So I essentially build up a huge matrix, and I start at the very top left. At the top left, I have two possibilities. Namely, I could try to find something like this. So let's assume that's the first amino acid of that first chain, and that's the first amino acid of the other chain. I have now three possibilities. I align this thing to this thing. Second possibility, I'll align this thing to a gap. Third possibility, I have this thing and align it to a gap, right? So essentially, if I now traverse my dynamic programming matrix, I could symbolify this as writing my matrix. I have three positions to which I can assign an arrow. I can go into this direction, or this direction. This direction means I align this guy to this guy. This direction means I align this guy to nothing, so a gap. And this direction means I align this guy to nothing. So far, so good? You're still with me? Yeah?
But I'm not sure because you're talking about aligning proteins, but I thought, like the context of the problem I'm thinking is like you're, let's say you got this pocket, so the docking context, and you're trying to, search through the space with your synthons.
Yeah.
And like, maybe you get some sort of pathological synthon that your docking algorithm finds and then gives the best score.
Okay, then give me a more minute. We still have a little bit of time. I quickly finish the similarity thing and then hop to the docking. So what we need to do is here, we need to find the best possible path through this dynamic programming matrix. And the dirt that you refer to in this algorithm or in this approach would be to avoid all this, because we only take a path like a motorway through this dynamic programming without looking to the left or right, which cannot be essentially. So now this is for proteins. For molecules, we would have to do this in all various directions and in multiple dimensions when you have branches, et cetera, et cetera. This is what I refer to with this hypercube. In docking now, the docking certainly can only be as good as the docking score. In our firm opinion, it is of utmost importance to include desolvation effects. Which means that when we have a pocket and we place something here, we must definitely try to be as good as we can with respect to capturing the desolvation effects for both the protein and the ligand. So we must be aware, if I have a carboxylate function in there, we must take an effort to desolvate it from the bulk water, and we need to do the same thing on the protein side. And then, yes, we have a problem because we have a dangling bond sticking out there where we don't really know what about the desolvation, what about the forces there. Yeah? Which is why in the algorithm we kind of dim down a little bit the energy contributions of this dangling bond, and then we build it up in a combinatorial way so that we cannot generate a rubbish reaction that doesn't even exist. So we can only operate on those reactions that have been used at the outset to define the chemical space. Does this answer the question now a little bit better?
It seems like a discussion.
Okay, the desolvation part, yeah. The solvation part. Yeah.
Okay. Lord, it's great talk as always, but my concern here is that your search is predicated on prior knowledge. We know this space is not, but that essentially means you are continuing to go with the negative. At no point do you ever probe that space to find out whether or not there is something new. I know that's expensive. I know it's dangerous. And I know the success rate is extremely low. Mm-hmm. But, again, drug discovery is a gambler's game with very low odds. Yeah. So
what you do, yeah. What you do is, well, at least what they tell me they do is they use tools like SpaceMax, which can extremely quickly probe for substructures, etc. And I imagine what they also would do is have a bunch of patent literature alongside and quickly check point checks, and then again feed this into a learning machine. But yes, checking for novelty needs definitely taken care of. Then again, the spaces are so big that by definition, most of the stuff is new. Yeah, at the very beginning, when we started out with this technology, we had lots of questions into the direction of, can I protect this? Yeah, can I really, I mean, if you set this up and you give this rule how to define something, will the attorneys not come, the patent lawyers not come and say, you have the rule there, so you can't really patent this anymore. It turns out that also the lawyers have understood that 10 to the 14th is not a rule that you can just write down and enumerate everything on. Yeah? So that's part one. Part two is usually these are not your final molecules that you really like to patent. You know, these are often starting points or refinements here and there, etc. So it's not really the stuff that directly comes out of the space and goes onto the table of the patent attorney. That's all I can say today. A good question, yeah. And thanks for the flowers, but
Hi.
hi there.
Just my question is in two-part, and it's interesting about the fragment where you're trying to grow the fragments and you got the 6 different crystal structures. So when you identify the weak binders, that pocket is completely open, or you induce that pocket by identifying the bigger compound. So when you identify the fragments, the pocket is already there, the large pocket, or it was induced by when you extended the more compound bigger.
So you mean for this fragment growing exercise with with crystals first?
Yeah.
So we started from the experiment. Whether there was some induction effect or not, cannot really, or we didn't determine. So we didn't take out the molecule and recrystallized again with the Arthor structure. So we didn't do that. But what we saw was the fragment was binding. The fragment was binding in the pocket as it was, and we used the pocket as it was and continued from there. Okay. So we did not take care of any sort of dynamics, for example. But people at Genentech, etc., they do. And I would also suggest you do if you know that your protein has a dynamic behavior or some lysine flipping in and out, etc. Please do consider using something like, I don't know, MMG-based.
Because many small fragments may bind on surface sort of pocket, like it's not completely open, right? Yeah,
but that's definitely why we also wanted to see the crystal. Yeah, and these were not pockets like this where the crystal, where the fragment was sitting on top. The fragment was well in the pocket.
Side.
Yeah,
okay.
Yeah, that was important for us.
Thank you.
Thank Marcus again. Thank you.
Thank you very much. And be our guests at CityTown. Thank you very much.